Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And as it turns out, this is going to be another pretty math intensive video. I actually didn't originally plan it to be that way, but I saw something on the web today which was a way of explaining one of the things I'm going to talk about, which I had never seen it explained quite that way, and I think it was really, really good. And there's no way to make sense of all that without equations. So again, if you despise math, it's probably time to find an alternate activity. So let me put myself down here in the corner, and we're going to talk about something called the geostrophic wind. Now, here are 6 isobars evenly spaced, okay? The low pressure is at the top, that's P, and then P plus 1, P plus 2, it gets progressively higher as you head farther south. So the pressure gradient force is always directed from high to low pressure, so that force is going to be going like this, and the Coriolis force is going to be to the right of whatever the wind direction is at a given time, 90 degrees to the right. So the pressure gradient force at all these different points is exactly the same. The arrows are all the same length because the isobars are evenly spaced, so no matter where you are in here, the pressure gradient force is going to be the same. However, the wind actually starts off blowing from south to north and then gradually curves around and ends up being west to east. Well, how does that happen? Well, when the pressure gradient force initially kicks in, the wind is going south to north, but the Coriolis force is proportional to the wind speed, and so it gradually ramps up. Gradually ramps up and is always 90 degrees to the right of the wind, and it eventually gets to the point where it's evenly balanced with the pressure gradient force, and so you have a straight west to east wind in this situation blowing parallel to the isobars, pressure gradient force here, Coriolis force here, and they balance each other, and that's called the geostrophic wind. Now, I'm sure you've all heard of something called the Cartesian coordinate system, which is basically an XY system. So if this is your wind, V, in this case a southwest wind, you can split that up into 2 components, the U component, which is along the x-axis, and the V component, which is along the y-axis, okay? So the U component is west to east, and the V component is south to north, but they're along the x and the y-axes. But there's another coordinate system in meteorology called natural coordinates. So we have the same southwest wind, but now N is going to be the axis that is 90 degrees to the left of the wind, okay? So that's going to be our N axis, if you will, in the natural coordinate system. So supposing we have an area of low pressure and we have a counterclockwise flow around that, N is going to be, at this point, to the left of the wind. So the wind would be out of the southeast here, and so N is going to be 90 degrees to that, to the left of the wind, so it would be blowing, or not blowing, N would be oriented toward the southwest, okay? R is always directed toward the origin. Well, what the heck do I mean by that? Well, for those of you that are young, this probably won't mean anything to you, but for those of you that are old like me, you might remember using a protractor in school, and you would put the sharp point of the protractor here, you'd extend the other arm out to this distance, and then you would spin it around and make a circle, okay? So the origin is the point of rotation, the center of rotation, and so that is here. So R is directed toward that center of rotation. So if N is positive going this direction and R is moving the same direction, that means that R is going to be positive, okay, with a low pressure area in the northern hemisphere. Now, with a high pressure area, the winds are clockwise. So at this point, the wind is going to be blowing from the northwest, okay, northwest to southeast. And so the wind, if N is 90 degrees to the left, it's going to be directed outward like this, but R is going to be pointed toward the origin, because even though it's a high pressure area now and the wind is going the opposite direction, the spinning point, the center of rotation, is still right in the middle, okay? So R is directed toward the origin, N is directed in the opposite direction. So if N is positive going this way and R is opposite to that, that means that R is negative in the case of a high pressure area, okay? So and we'll review this again in just a bit, but for a low, R is positive, for a high, R is negative. Now, this is called the momentum equation, and it basically states that V squared over R, which is the centrifugal force, that's the force that is trying to pull the air out away from that circular motion, okay? And you experience this when you make a turn in a car, especially if you make that turn too fast. You feel something sort of pulling you away from that turn that you're trying to make. But in the end, if all goes well, you end up successfully making the turn. So that's that force. Then the Coriolis force is the product of what we call the Coriolis parameter times the wind. Coriolis parameter is proportional to the latitude. So the farther north you go and the greater the latitude is, the stronger the Coriolis parameter is and the stronger the Coriolis force is, okay? So that's that, and then this is the pressure gradient force, which is the change in pressure along the n-axis, okay, which points 90 degrees to the left of the wind. Okay, so for straight flow, R is 0 because you can't take a protractor and ever make a straight line with it. It's always going to have at least some curvature. So if R is 0, that means that V squared over R is undefined. You can't divide anything by 0. And so what you're left with is this. The Coriolis force is equal to the pressure gradient force, and the reason the minus there, it's simply a way of showing you that one force is operating in one direction and the other force is operating in the other direction. It's just a symbolic way of indicating that. So the Coriolis force is balanced with the pressure gradient force, and we call that the geostrophic wind, okay? It's the most basic of winds in meteorology. Now, if the flow is curved, then the actual wind is not geostrophic, but what we call ageostrophic. And really, most of the weather that we experience, weather of substance, is because of ageostrophic components to the wind. If everything was balanced, the weather would be very boring a good bit of the time, okay? So it's the ageostrophic wind that comes into play that really makes a lot of our sensible weather. So let's take a look at this equation here, the centrifugal force, the Coriolis force, and the pressure gradient force. Now, V squared over R, okay, R now actually has a value, so we can't take that term out of the equation. And what we're going to do here is split the Coriolis force into two components, one with the geostrophic wind and one with the ageostrophic wind, and that's going to equal the total wind, okay? And so you have three terms now, the centrifugal force plus the Coriolis parameter with the geostrophic wind, the Coriolis parameter with the ageostrophic wind, and that's equal to the pressure gradient force. Now, we know from before that the geostrophic wind is balanced with the pressure gradient force, right? Okay? Or the Coriolis force is balanced with the pressure gradient force. And so we can knock out these two terms, okay, because they balance each other. And so now, what are we left with? We're left with the centrifugal force equal to the ageostrophic part of the Coriolis force. Okay, you with me so far? So it's the ageostrophic part of the Coriolis force which is balancing the centrifugal force. So here's that equation once again. So if the centrifugal force is equal to the ageostrophic portion of the Coriolis force, around a low pressure area, R points toward the center of curvature, which in this case is the same direction as N, so R is positive. We talked about that before. With a low, R is positive. Around a high pressure area, R points toward the center of curvature, which is in the opposite direction of N, and so R is negative, okay? And we talked about that before, R being negative with a high pressure area. So, if V squared over R is equal to minus FV, the ageostrophic part of the Coriolis force, if R is positive, that means the left side of the equation has to be positive, and so the right side has to be positive as well. Well, we've already got a minus sign there, so we've got to have another minus to make the entire side of that equation plus. So that means that the ageostrophic wind, V sub Ag, has got to be less than 0. It's got to be negative to cancel out the other negative and make the right side of the equation positive like the left side of the equation is, okay? So if the total wind is equal to the geostrophic wind plus the ageostrophic wind, and the ageostrophic wind is negative, that means that the total wind has to be less than the geostrophic wind, or what we call subgeostrophic. So with a low pressure area, the winds end up being less than the geostrophic wind if you were to calculate what the geostrophic wind is. Okay, so the winds are a little bit weaker than geostrophic. Now, here's the same equation again, but this time around the high pressure area, R is negative. So that means the left side of the equation is going to be negative, so the right side has to be negative as well. Well, we've already got a minus sign there, right? So we don't need any more minus signs. And so that means that the ageostrophic wind, VAG, has got to be positive, okay? Because if we had a negative, negative would make plus, and that wouldn't match the left side of the equation. So the ageostrophic wind, in this case, is going to be greater than 0. But again, the total wind is equal to the geostrophic wind plus the ageostrophic wind. And if the ageostrophic wind is greater than 0, that means that V has to be greater than the geostrophic wind, or what we call super geostrophic, okay? So if you think about an upper air map, maybe where we have like a big ridge like this, and then it turns anticyclonically, and then it goes down and curves cyclonically in a trough. The winds in the part of the flow that is anticyclonic in the ridge are going to be greater than the geostrophic wind, and in the belly of the trough, they're going to be less than the geostrophic wind, okay? And so you end up getting convergent patterns. If you have a stronger wind in the ridge and a weaker wind in the trough, then you're going to get convergence, speed convergence, because you have a strong wind blowing into a weaker wind. And then on the east side of the trough, then you're going to have the weaker wind, and then you have, as you go up toward the next ridge, a super geostrophic wind, so you're going to have speed divergence there because you have stronger winds and weaker winds, and the stronger winds are blowing away from the weaker winds, so you have divergence going on there. And again, if you have divergence in the upper levels of the atmosphere, you have convergence in the low levels and vice versa. So these ageostrophic components really have a significant impact on the sensible weather. And again, if everything was balanced, the weather would not be very exciting at all, but it's the imbalances that really make most of the interesting, quote unquote, weather that we experience on a day-to-day basis. Okay, I know that was a lot of math. I hope it made a little bit of sense. That is bonus weather video number 2 for this week. The next one will be coming up on Friday, and the next daily weather update, of course, coming up tomorrow, both the short and the long version. Hope you have a wonderful Wednesday evening, folks, and we will talk to you again tomorrow. See you later.